Hi, welcome to Chapter 8 and 9 Bonding, Overview Part 3, where we're going to talk about exceptions to the octet rule and resonance structures. So, exceptions to the octet rule. There are three types of ions or molecules that do not follow the octet rule. An ion or a molecule that has an odd number of electrons. An ion or a molecule with less than an octet. An ion or a molecule with more than 8 valence electrons. The ones that normally will do less than an octet are boron and beryllium. So anything that is less than carbon. And the ones that will do more than 8 are normally in rows 3, 4, 5, 6, 7, and 8. Okay. So row 3 and lower on the periodic table. So let's look at the odd number of electrons first. There's just nothing you could do. When you have an odd number of electrons, you can't pair them up. If you notice, every time we draw Lewis structures, we're always drawing them in twos. Either they're lone pairs or they're a bond of two. So these are quite unstable, and you end up with a molecule with an odd number of electrons. So here is two examples. Which one would be your preferred structure using formal charge? So let's look here. Let's write our valence electrons. So nitrogen has 5, oxygen has 6. Minus, so we have 3 dots, 1, 2, 3, and 2 lines. So minus 5. So that gives us 0. Here, 1, 2, 3, 4, 5, 6. Okay, now let's look at this one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Now, what I didn't say in the last video is your formal charges have to add up to whatever charge is on your molecule. So in this case, they both add up to 0 because there is no charge. But remember from our last video, the structure that gives you a formal charge closest to 0 is the more preferred one, and that would be this one. So fewer than 8 electrons. So elements in the second period before carbon can make stable compounds with fewer than 8 electrons. So let's consider boron BF3 here, okay? Given boron a filled octet, we'll place a negative charge on boron. So here we have filled octet, filled octet, filled octet. All of them have a negative charge on boron and a positive charge on fluorine. Now remember, fluorine is the most electronegative element. And what did we say about what type of formal charge should your higher electronegative element have? It should have a negative charge. So since this is a positive charge, then these here are less stable. Maybe not stable is the right word. Less important. So this would not be an accurate picture of the distribution of electrons in BF3. So these are really wrong. So therefore, the structures that put a double bond between boron and fluorine are much less important than the one that just leaves boron with 6. Let's check the formal charges on here. Okay, so we have boron and fluorine. So boron has a valence of 3. Fluorine has a valence of 7. Each fluorine has 6 dots and a bond. Boron has 3 lines coming off. So when you subtract these, you get formal charges of 0. So this is your more preferred structure. So if filling the octet of the central atom results in a negative formal charge on the central atom and a positive formal charge on the more electronegative atoms, then you're not going to, then do not fill the octet. Okay? Because remember, your most electronegative element should have a negative charge on it, not a positive. Sometimes we can have more than 8. And sometimes we call this the expanded octet. Because it has more than 8. And this normally happens with elements in the third period and below on the periodic table. Okay, so you see here, phosphorus has 5 chlorines coming off, so that's 10 electrons. That's more than 8. Okay, why may this be allowed? Well, as it turns out, because the P atom is large enough, so it is larger than the row 2 elements, it can kind of fit these 5 chlorines without them being overcrowded. In contrast, if you look at the second period elements, they're just too small to fit 5 atoms around. But if you're going to have an expanded octet, if it does occur, most often you're going to be bonded with the smallest and most electronegative elements, which is fluorine, chlorine, and oxygen. That's not to say you can't have an expanded octet that's bonded to a different element, but these are the most common that will occur. So when we have more than 8, we call this hypervalent. So in your periods 3 to 6, your atoms can use the d orbital to make more than 4 bonds. So that's why they're called hypervalent. And that's what you see here. Okay. Here we have 2 Lewis structures for phosphate. And they have the formal charges already listed on there. So this one here has a completed octet. This one has an expanded octet. Based on your formal charges, which one is the more preferred? Well, here you have a lot more charges. Here you have some zeros. Remember, it has to add up to -3. So this structure here is the more preferred. So it's more preferred to expand the octet and reduce the formal charges than having more formal charges. So even though we could draw a Lewis structure for phosphate ions that only has 8 electrons around the center, the better structure puts a double bond between the phosphorus and one of the oxygens. Right here, double bond. This eliminates the charge on phosphorus and the charge on one of the oxygens. So you're getting less charges here. Okay? So what is the lesson that we learned? When the center atom is on the 3rd row or below, and expanding its octet will eliminate some formal charges, then you want to do it. You want to do that. So you would prefer to expand your octet and reduce your formal charges. Now there's something called resonance, and you might remember this from chemistry your sophomore year. And that's when you could draw more than one Lewis structure, okay, that could kind of depict the structure, whereas not one of them is correct, but the combination of both of them is correct. So here you could use multiple structures called resonance structures to describe a molecule. Resonance is when it's possible to draw the same structure of a molecule, but you're moving a bonded pair of electrons. So here are 2 possibilities for ozone. And really what's happening is ozone is really an average of these 2. So you can't say it's this, and you can't say it's that. So you have to show both of them because it's kind of an average of the 2. And when they measure the bond length of ozone, they find that the bond lengths are the same. Look here. Does that make sense? Well, you know that a double bond is shorter than a single bond. So how can these bond lengths over here be the same? Because it's not like a distinct double bond here and a single bond and a single bond and double bond. It's kind of like you're averaging them over each other. So really what you have is kind of like 1.5 bonds on each side. So that's why you could get equal bond lengths. So one Lewis structure cannot accurately depict the molecules, such as ozone. So you need multiple structures to show the resonance structures. So normally you'll draw both of these and put like an arrow between to show that both of these are kind of like the averaging of them. And the bond length is really what tells you that the ozone is kind of an average of both of them, because otherwise one bond, the single bond, should be longer than the double bond. So here's another example. So in truth, the electrons that form the second double bond here between carbon and oxygen, they do not always sit between the carbon and oxygen, but they can move around among these. So they move from here to here, here to here, here to here. Okay, so when they can move around, we call that a delocalization of the electrons. When they are staying there, so like the electron here, this is localized. It's staying here. This one, because it could kind of go back and forth, is a delocalized. So you'll see a lot of resonance structures in organic molecules. So here's an example of benzene, and you see you have this alternating double bond. So how is it represented when you're drawing it? Well, in organic chem, sometimes they'll draw this like hexagon and they'll show the double bond here and here and then draw an arrow between. Or they'll just put a circle showing that the double bond is alternating. So again, localized electrons are specifically on one atom or shared between two atoms. They kind of like stay in that general area. If you have a delocalized electron, they could be shared by multiple atoms. They could kind of jump around. So let's do an example of this. So draw the Lewis dot structure for nitrate ions. Remember, nitrate is NO3 with a -1. So the first thing you want to do is add up your valence electrons. So nitrogen has 5 valence electrons. Each oxygen has 6. And then you have an extra one because you have a negative sign here. So when you add them all up, you have 24. And you know nitrogen is going to be in the middle. So here you have your 3 oxygens around nitrogen in the middle. So let's put some dots here. So far we use 6. That leaves 18. Two, 4, 6, 8, 10, 12, 14, 16, 18. So I used up all my valence electrons. But did I satisfy the octet rule? Remember, nitrogen, carbon, nitrogen, oxygen, and fluorine, they satisfy the octet rule. Okay, so this should be satisfying the octet rule. Are there 8 around nitrogen? No. So I have to do something. So I have to take one of my lone pair electrons and make a double bond. So now, are there 8 around nitrogen? Yes. Are there 8 around oxygen? 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. So now my octet rule is satisfied. Okay? But can you visualize, and we kind of have to put this in brackets with a negative sign because it has a -1. Can you visualize some other possible ways of drawing this structure? Sure, that double bond can move. And there's one more. So there are 3 resonance structures here. Just for the fun of it, let's calculate the formal charges. Okay, so we have oxygen and nitrogen. So here my oxygen has 6 valence and nitrogen has 5. Those are your valence. So keep that in mind. So this nitrogen has 4. So 5 minus 4 gives me a plus 1. And this nitrogen has 1, 2, 3, 4, 5, 6. So that has a 0. This one has 1, 2, 3, 4, 5, 6, 7. So that has a minus 1. And this one has a minus 1. So when I add up all of these charges, I get minus 1, which is on my polyatomic. And there's really nothing I could do to minimize my formal charges, because remember, nitrogen cannot form an expanded octet. If this was something in period 3, then we could expand the octet to reduce our formal charges. So that is it for expanded octets, incomplete octets, and resonance.